This podcast is supported by Siemens, your partner for industrial-grade AI.
Hi there, welcome to a new episode of the Industrial AI podcast. My name is Peter Seberg and I'm your host. Today I'm going to be talking to, once again, Oliver Niggemann, Professor for Computer Science in Mechanical Engineering. Oliver Niggemann, that is, from the University of the Armed Forces in Hamburg. And today's topic is going to be numerical machine learning. Hello, Oliver.
Hi, Peter. How are you doing?
I'm doing just fine. I already had breakfast. You just said you hadn't even had time for breakfast. I'm not going to tell and share with the people out there what time it is, but you should take care of yourself and have breakfast in the morning, Oliver.
You can see what kind of stressy job this is.
Yeah, right. Okay, that was a very good introduction. Please tell a little bit more about yourself, Oliver. Please introduce yourself to our listeners.
Yeah, I cut a long story short. So actually, I'm really focusing here on, we have a professorship and a research institute focusing on AI. And I personally mainly research in the area of using AI or AI methods which are suitable for technical systems, for engineering problems and material science problems. So and then automatically we need methods which are very, very reliable and trustworthy.
And that's what we're going to be talking about today. Now, we already did 2 or 3, I think, podcasts. I know I look back, the last one we did, it's about a little bit over 2 years back. That was in the summer of 23. Do you recall what that was about?
Probably AI, but I really don't remember any details.
Okay, here's an external person testing the professor. It was about robustness and generalization performance of deep learning models on cyber physical systems. I know that's a term that you have been using. Maybe we get to that a little bit later. So that's what we did at that time. Today, we're going to be talking about numerical machine learning. And I'm going to promise you, dear listener, I'm not a big fan of deep mathematics. This topic does have a lot of deep mathematics, but that's what we are not going to discuss today. Still, I do believe that it is important for us, for you listeners in the Industrial AI podcast, what this topic is all about. Now, I had read and asked you, Oliver, about a kickoff meeting, and that was for the extension of the project KISS, K-I-S-S, and I believe that is AI for diagnosing the International Space Station. So you met with, amongst others, Airbus defense and space people. I hope that I'm not saying things that people are not supposed to know. If not, we're just going to cut it out. And I wanted to know from you if the project maybe was going to bring you close to Munich, south of Munich. Actually, I'm not that far away from where the Airbus defense head office is. You gave a different city as an answer, but maybe as a start, you want to tell us, if you can, a little bit about that project.
Yeah, that's a very nice project because we can rely on all those years of ISS data. And that's one of the very nice things about the space station is, first of all, that we have the recordings of years of sensor data there. And we are focusing on the Columbus module. And so we analyze the sensor data there. And we, first of all, do a lot of anomaly detection. Can we automatically, using machine learning, analyze those sensor data? And can we find anomalies, let's say, important points in the data where a human operator has to look at? And since it's a space station, it's also a very nice example for diagnosis. I mean, even if you see an anomaly, you normally would like to find out very, very quickly what's wrong, what should I do? And that's diagnosis, which is much more difficult than anomaly detection.
Which is very interesting. You say you have access to a couple of years back. My brain brings me immediately to a situation at the very, very beginning of my, let's say, data science. And that's when you and I have been doing trainings, and I recall that we got years of data. Now, does that mean that typically today the data is be diagnosed off-site? Is there an expectation with changing systems, things getting smaller and smaller and smaller, that what it is that you will learn today, that maybe in the near future they can do that actually in space?
Yes, I mean, it's always for space, it's always for avionics. But at the end of the day, if you talk about chips, we have the same problems there. You need some edge processing. And the goal definitely is to do a lot of those processing steps on board. Here for the ISS, we still do it offline. And it's not a big issue there, because there we really focusing on the second level support. So if something really serious happens, then you have people in second level support who to take care of that at Airbus. And so we're helping them. But if we talk about general, we have like projects, obviously with the Navy here, we are the University of the Armed Forces, but we also have problems like with the German search and rescue team, so DGZS in Germany. And there on a ship, you have the same issues. You want to be very, very sure that even if you don't have any communication means, you can still operate. And obviously in a military setup, for several reasons, you have the same problem. So at the end, we talk about a combination of cloud and edge, of IT and OT with all those cases.
Very interesting. I'm not going to get into the details. We will do that afterwards when we talk friendly, because there's a couple of guys actually, and I've shared with our listeners that I'm in a Bavarian band playing typical Bavarian baritone, and we have the other University of the Armed Forces, and some of you listeners may recall. So the one is in Hamburg, where Oliver is, and the other one is actually in the village south of Munich, where I am. There's a couple of guys there, and they are being trained on, what are they called? The ships that go in the sea, under the water. And I hear every now and then things that they are allowed to talk about. That's not always. So I learned that in space, you've been working with symbolic AI. That's a topic I've become interested in lately as well, towards neuro AI. Maybe we talk about that later. But the topic of today is a different one. You did a presentation at Fraunhofer, one of the many Fraunhofers, IOSB, Institute of Optronics System Technologies, Image Exploitation. I understand it's your former employer. You can talk about that. And the topic you did, and that's what we're going to be talking about today, is numerical machine learning. So you shared your paper on exactly that topic, numerical machine learning. I said, looks great, but we're not going to discuss differential equations. So Oliver, as I said before, the majority of our listeners are not scientists. Maybe some of you love mathematics, very deep mathematics. Many of the listeners do not. Nevertheless, so we want to get a first understanding of what this is about. Please give us an introduction, Oliver.
Yeah, just to make an advertisement for differential equation, they are much more fun than they sound. So differential equations can be a lot of fun. And by the way, I just was spending Friday night with my son in his high school, in his school. And they had a long night of mathematics. So I actually saw dozens of young students between 10 and 16 years having fun also with differential equations the whole night. So just to emphasize this, differential equations can be a lot of fun. But to come back to your question. So in general, we are still very close to what we talked with the KISS project. We need to combine sub-symbolic machine learning style AI with symbolic AI. Why? I mean, first of all, we do have a lot of, at least in engineering and material science, in physical problems, we do have a lot of models which humans create or humans understand. And they're symbolic. They're formulas. They're math. And math is our way of formalizing in a symbolic manner our world. That's actually what math is about. On the other hand, we have all this data, machine learning, deep learning stuff. And we can use those models. We can use the knowledge we have to improve machine learning, because the more knowledge you put into machine learning, the less data you need, and the more robust, the more out of distribution can you learn. So there is a lot of reasons to combine this. And also the other way is very important. If you have a machine learning trained model, you can put it back into a symbolic world, which engineers, which scientists understand. So we need this combination of both worlds. And that's very much what we talked about there. Here with Fraunhofer, we're doing a lot of nice research there. And in general, in my professorship, we do have a lot of projects where we try to use AI for surrogate models. That's what this talk was about. And surrogates model is, just think about, you would like to develop some hydrogen storage, or you would like to develop some foils for airplanes, or you would like to develop some materials, and normally what you use is a simulation, a very time-consuming simulation. And we do have one of very, very large APC here in Hamburg. And still, if my colleagues do one of those simulations, material science simulations, or simulations of airplanes or whatever, then this takes days or weeks. And then you have only simulated a single configuration. And what we would like to do is we would like to create a neural network, a machine learning model, which replaces this simulation. We call it then a surrogate model. And this surrogate model obviously is definitely worse. The quality of the results is worse than a good partial differential simulation model, but it's much quicker. So instead of investing days, you're investing minutes. And that means you can simulate a lot of different configurations. So if you're looking for a new battery configuration or a new hydrogen storage configuration, a better foil structure, just pick your poison. And so you can go through this configuration, through this design space very, very quickly. And once you find a good solution, you can say, hey, now I do a high quality, time consuming simulation. So surrogate models is definitely one of the hottest topics in AI currently, I think.
Right. Yeah. But we're talking terminology here. So because you're kind of opening my eyes, not sure those of the listeners I cannot see, but I started saying, you were using symbolic AI in space. We're not going to do that. And then you're saying, well, you are combining. So because I understand combining what, in my understanding, is symbolic AI. And for me, symbolic AI is the AI from the first 10, 20 years, 60s, 70s, 80s of the 1900, right? And it was about, I see a chair here, I see a table, I see a graph, and that's what's for me symbolic. Are you saying that what you're doing is in a different term, neuro-symbolic, but you're not using that term, you're using a different term? You say numerical machine learning?
To some point, it's related. Numerical machine learning is a little bit more specialized. You're right. I'm a little bit avoiding the term neurosymbolic because that the term fits because it somehow expresses this combination between neural and symbolic. So it's a nice term. It's a little bit used for a specific family of algorithms. So I think it's a little bit used in an ambivalent manner. So you can use it to say, hey, we need to combine symbolic AI and subsymbolic AI, neurosymbolic. But it's also more and more used for a specific family of methods. And so I'm a little bit avoiding this because it leads to misunderstandings at some point. But you could call it like this, yeah.
Very, very good. Very interesting because I was writing just an hour ago on the very, very same topic and for the very same reason, the term neurosymbolic AI is to be not used for exactly the same reasons that you're saying. Okay, let's move on here. So the paper that you wrote together with, always like calling out names, but they always put a lot of work into it, Maria Maleshkova, I hope I say that correctly, Anne Jung, Dennis Kramer, and Bernd Zimmering. I saw those names on the paper together with yours, Oliver. You describe 3 classes, solution methods for numerical machine learning. So maybe if you can, share them with us, maybe to give us an overview and then go a little bit detail, not too detailed, as I said.
Yeah, maybe give them to outline maybe a little bit what this is about. So if you do a surrogate model, so you replace a numerical simulation, then what you normally do, you create a model which is replacing a single simulation step. How does such a simulation work? You start with a specific configuration for the flow of some liquids or for some thermodynamic configuration, and you start with a specific situation. For example, we have a project where we build surrogate models for burning buildings. So you have a burning building and you would like to know how the heat, how the fire is changing over time. Because if you know that, you could, for example, derive where is it safe for a fireman, where is a risk. So just take this as a maybe more illustrative example. And then you start with a specific configuration. You have a room and a small fire in one part of the room. And now the simulation continues or works step by step. So it simulates a millisecond, and then it has a new situation, a new configuration of the room what is the temperature in which small part of the room. And then you proceed like from step by step, 1 millisecond after 1 millisecond. And each new step is computed as the change in comparison to the previous time step. So it's a step by step. Now, the problem with those simulations is if you have a small error somewhere, this error is summing up. It gets larger because you only compute the changes. And that's what we call, your favorite, Peter, a differential equation. And so we're back at differential equation. And there are a lot of nice algorithms in AI which sort of use models. We do have some knowledge about how this works. So we take a neural network, but we give additional symbolic information to this neural network. For example, pins are a very famous example, very great algorithms, which do that. Now, what we did is, and what we do in several projects, and what all those great researchers you mentioned here are doing, we go a step further. The methods we are working on, they do not only use a neural network to compute the change in comparison to the previous time steps, but whenever you do a time step, the training of the neural network can go all through back in time through the whole number of previous time steps. So if you are in a specific situation, so you have prognosis or simulation with a surrogate model of 100 time steps, if you use this neural network and it sees the error is getting too large, it can correct the whole 100 previous time steps. So those methods integrate normally this numerical stuff, step by step, and it adds those step-by-step behavior into the neural network. So previously, we very often had this step-by-step stuff, and we replaced one step, the simulation, with a surrogate model with a neural network. And now we input this numerical behavior, the step-by-step procedure, into the neural network. And now this is, instead of having like two separate things, the step-by-step thing, which we call the integrator, and the surrogate model, and we integrated this. A lot of other people did, not only here in Hamburg. There's a lot of previous work on that. But we use it to create more stable, more robust surrogate models, for example, for this fire simulation.
Okay, I heard you mentioned pins. Are they the physics-informed networks?
Exactly.
And if so, are they again a subset of the numerical approaches?
They are one of the numerical machine learning approaches. There you sort of regularize, you add additional information to a single step. And those numerical methods we talked about, for example, in this presentation with Fraunhofer, they extend this to a lot of time steps. And if a simulation has like 1 million time steps, you can imagine by removing those small numerical errors or making them smaller, we have a much more stable simulation. And there is currently a lot of work, especially in material science, going on for high quality surrogate models. Because if you're looking for a new battery, and you can check thousands of configurations instead of a single one, you have a very big advantage in design of new batteries, new storage for hydrogen, whatever.
That's, I believe, is one of the areas. And we're going to be talking about areas, use cases, applications in a minute. So if I understand correctly, the pins, they're going to have whatever laws of physics, so about fluids and earth and strengths and whatever we have, most of us in the engineering world have learned as somewhere. So that information that in the last, not only 100 years, maybe it's even 2000 years, but whatever we have learned about Earth and the physics around us, we have put them into laws typically, and that information is being represented then through the pins or into the pins. Is that the way it works?
Exactly. So all the numerical, all the continuous approaches, they all add a specific, this knowledge is added to the neural network. And then we have very different ways of doing that. Pins usually do that for a single step of such a optimization. And then there are a lot of new methods around which further optimize this. And for example, also put this numerical stuff, the simulation, the step-by-step, the integration part, they also add this to the neural network. So what we are seeing is that more and more, not only the knowledge about the physics, but also the knowledge about the simulation itself, this integration is now also added to the neural networks. And which means that the neural networks know much more, not only about the physics, but also how the physics is used for simulation. We add all this knowledge to the neural network, and the more knowledge the neural network has, the better its results.
Right. Okay. I'm going to ask you at the very end what that means as a professor and students, what students need to learn. But I want to keep that to the end, because for now, I thank you. I'm still with you, and I'm very hopeful the majority of listeners as well. So thank you for not having gone too deeply. Now let's look at what the typical use cases, what the applications are of numerical machine learning. Can you share a couple of us?
Yes, I mean, we had this very nice example with the burning rooms. There we have a surrogate model, a replacement of a simulation for thermodynamics. So how is heat sort of moving in a burning room? You can also use it if you optimize like batteries. In battery design, you have to optimize the surfaces. You have to optimize the behavior of the materials in the battery. So it's hydrogen storage is a very nice example for that. But also, if you talk, for example, about the construction design of new things. So we have a very close cooperation, for example, with my colleague Professor Weber here, and there we talk about the design of new bridges. It's static. How is the static of a new bridge? Or we have a very nice cooperation with Professor and he's doing the weirs. So how if you have like a river construction in the rivers. And there you have to optimize the weirs, the water construction. You have to optimize this according to the flow, which is very hard to simulate, and neural networks can replace that. I mean, Peter, so I don't have to explain to you how important weirs and stuff is, right?
Oliver knows that I studied at least a couple of years civil engineering in Delft, a lot to do with water, and Oliver himself personally spends a lot of time on the water, on the Dutch water. Some very nice examples, yeah. And the one with the bridges brings me almost like to a personal hobby of mine. What is a hobby is a little bit strong, but seeing bridges already when driving around I always get completely fascinated. What about, I read in the paper, material design, which is one that we read and hear about a lot these days in general.
Yes, material design, batteries or hydrogen storage is a nice example. And then you have to optimize the materials. You need specific materials which have a specific adsorption behavior. And you can do this on different scales. We do that on a macro scale, but also with some colleagues, Professor Kramer, for example, and he's deeply into the atomic simulation stuff. Then you really optimize the atoms. So he's trying to explain that to me to some extent. That's also totally beyond my my field of expertise. Because I'm not a chemist and I'm not a physicist. But you can use the same neural ODE and the same numerical machine learning methods to optimize atomic simulations. And then that's really amazing. They really simulate the single behavior of atomic particles. And that's really very, very cool stuff. And I think there we'll see a lot of great developments in the next 10 years.
Yeah, and I'm going to read, if I may, a quote, one line out of your paper, which is exactly about atomistic length scales. Neural networks are at the cusps of matching mean field approximation, etc. And the reason I do this, and Robert, my co-producer, will immediately know what I'm talking about, because there is this startup called Cusp.ai, which we are closely linked to, Amsterdam, and Cusp.ai is a frontier AI company on a mission to solve the breakthrough materials needed to power human progress. They're not just some startup. They have, just to mention, Jeffrey Hinton and Jan LeCun as their advisors. Now, there you go. A cusp. Do you know then what I looked at what a cusp is, and I saw there was like a picture of a curve where a moving point must reverse direction. It looked like a bird to me, like with two wings, and the point where it's connected, one goes to the left and the other to the right. So that's very interesting. Now, we've discussed it many times, Robert and I as well, and whenever we do our conferences, there's many times about, I'm never really sure. It depends a lot on the people who do that. Now, you gave already two examples, or you gave the example of the battery design as a typical example. So you say engineers. So if we say we design cars and then maybe we buy batteries, or maybe we decide that we're going to produce our own battery, and that's already where you say I can use this technology to come up with the best possible solution for my battery.
Exactly. And then what would be the normal design process for this? Somebody, a physicist, a chemist, engineer would create manually a new design and then check it using simulations, using it experiments. And I think the problem we currently have is simply to check one specific design, it takes a long time. And the more configuration possibilities you have, the larger the search space. So the more problems this approach has. And so all we are trying to do is speed up this design process by having automatic design, an AI-based design at the end. And surrogate models are one of the key enablers for this, because you can very quickly check new configurations, new designs. And if we are leveraging this, then there are so many possibilities for new designs, for materials, for vehicles, for structures.
Proteins, maybe.
Yeah, proteins. I never really did that, but that's, I think, also a very, very big application for medicine.
May we assume that what Google DeepMind has been doing, and where Demis Hassabis got the Nobel Prize for, with proteins, it's a very similar approach, but maybe it's too far to just assume that at least it is in the same direction of trying to look into what, and you say even at a atomic, or in this case protein level, what new solutions can bring for us.
Yeah, exactly. But then again, I think this shows this to be successful in this area, you definitely need two things. You need an interdisciplinary research approach. It makes I can do the AI algorithms, but I have no clue about the application field. It's not a good clue at the end, not in a scientific manner. So I have to talk with my colleagues here, and you really need research institutes with an interdisciplinary approach, and that's why. What we really do here at the university, we have a very nice climate for interdisciplinary research. And the second thing you need is a lot of computation power, and I really mean a lot of. And we also have a large HPC here. And so to be successful in this area, and we need those two enablers. And I'm not really sure whether we have established this in all places.
Sure. If I'm correct, it's I'm not sure it's the final, but at least it's like the closing of your paper. You say exactly that you say algorithms have to be transferred from machine learning to the domains, physics, chemistry, and engineering. So that is what you're suggesting to the listeners as well.
Exactly. I think if one of the listeners is thinking about going into science, go into interdisciplinary research. I know there are a lot of people telling you stick to your topic, do AI algorithms, do physics, but most of the good stuff, I think, is between those fields. It's in combining those fields. That's, I think, where the new success stories in the next 10 years will be. But this is difficult because if you're from a research point of view, if you're working in 2 fields, 3 fields at the same time, it's not good for your statistics, because you normally are much more
really
successful. If you look at the Hirsch index or stuff like that, then you should stick to one field. But and this is what people at universities very often look at. But if you look to the US or to Asia, then you see the people are much more interdisciplinary.
Yeah, but then we need to change that, right?
We have to change that, really.
I mean, not me, but you and the people in the universities. I mean, I recall I was the first. That's many, many years back, as you know, when I finished. And I studied within civil engineering, architecture, and then I combined with informatics, right? So we called it computer-aided architecture design. I was the first person. I not know if there was ever a second person, but that was also like a special thing. But I never really considered, was that going to be negative, looking in a negative way for what I've been doing. And at least there's many of these combined studies within the world in which you operate as well, I assume, these days. Or
Yeah, that's definitely. Here we have a lot of cooperations with different fields, and I think that's really it's a lot of fun, and that's really where you also can create new methods and new algorithms. But look at my professorship. This is an AI professorship in a mechanical and civil engineering department. There are so many computer science AI professorships in mechanical and civil engineering departments. Normally, you just put them in the computer science departments, and they stick to themselves. I'm a little bit exaggerating.
I mentioned Jeff Hinton, just a year ago, he got a Nobel Prize within the physics world. And people were saying, what is that all about? Isn't he one of the guys who laid the groundwork, some of the groundwork for artificial intelligence, for machine learning? Oliver, you talked about the space station, very interesting. Maybe you can share 1-2 more projects, and then I saw the beginning of your presentation, and we already talked a little bit about symbolic AI. You do all kind of diagnosis, recurrent neural networks. You work with graphs. We talked about pins, neural planning. If you can share maybe 1 or 2 other projects that you have been working on that may be interesting for us, and just tell us what is the type of machine learning, artificial intelligence that you have been using.
Yeah, sure. So, I mean, the bread and butter in our field still, if you look at the kind of projects, there is obviously a lot of anomaly detection, prognosis, condition monitoring, predictive maintenance. That's still an important topic. For example, if we talk about the ships, then talking about the ship projects, we do a lot of edge processing in ships and trying to analyze sensor data, making sense of the sensor data, finding patterns, using it for predictive maintenance stuff. So we have a very nice project. We talked about that search and rescue organization in Germany, the DGZS. And that's a very, very nice project because we also try to, for example, automatically find people in the water or track people in the water. And also analyze the sensor data itself of the ship. So that's a very typical project we are doing here. And the other thing we are doing more and more, I think the majority of our projects are civil, but I think that's also a very nice development we are seeing. We do more and more dual use AI projects where we combine civil applications with military applications. And that's something the Helmut Schmidt University, as University of the Armed Forces, obviously is well suited to do that. And there we do a lot of intelligence stuff where we analyze data for analyzing military situations. And I think this is also a very interesting development that we are seeing in Germany more and more dual use research, and which is very traditional. And in the US, they have been doing that for 30, 40 years. And we also see that also the typical situation awareness, situation assessment for military applications would be another very typical project we are currently doing here.
Okay, well, yeah, and then we know, at least in Europe, in Germany specifically, there's a lot of development, a lot of investment into defense, which I guess directly, indirectly moves your direction. So let me ask you, tell us about your team. What is the kind of job roles you have in your team? Where are you based? Are you looking for talent? And if so, what should they bring?
Yes, we're always looking for talent. So if you're out there hearing this podcast, look for a great way to do your PhD. But be welcome to contact us. What we are normally looking at, we do have people from a lot of different backgrounds, and we're back to this interdisciplinary idea. I have a lot of engineers, mechanical engineers, other engineers. I have a lot of people from the field of mathematics or computer science. So we have one person from the field of biology, where we, for example, try to analyze, and again, it's a surrogate model at the end of the day. We try to analyze how the farming configuration, how do you farm, how do you work on the field, how does it influence the biodiversity? Again, this is differential equation. We always come back to that, but there we do a prognosis for species numbers, for how many birds, etc. are there. So we have also here a PhD student who's doing biology. So this is really an interdisciplinary field, but still, at the end, you have to be very interested in the AI algorithms, because our goal is to develop robust AI methods. That's really our main research field. So you definitely you need to like differential equations and math.
Right, not like Peter.
Yeah, I wouldn't hire you, Peter. No offense, man.
Now, final question: what is then numerical machine learning going to do to our world? I mean that in a positive sense, of course. What is it going to change? What is it going to change not only when your students are finished, maybe some of them stay with you, others go into the world and do things, but I mean also specifically, I already mentioned it, what does that mean to what it is that your students are learning today? And when I was thinking about it, when I said, so when we're now going to put all the physics that we learned, the last 100 or 2,000 years, and in the past, when we did an engineering study, maybe the first year or the first 2 years were full of, learning about the world around us. Is that going to change because you say, well, the people interested in what they need to learn is all this machine learning, the numerical machine learning, other forms of artificial intelligence. So if you're going to put that into their roster, you need to take something out. Are they going to learn less physics in relation to what you learned or what I learned in the past?
That's a very good question. And that's a question which is not answered at universities so far. I mean, classically, universities train people for specific, very traditional fields like mechanical engineering. And now you have separate AI. So we just start in 2 years with a nice bachelor and master's in AI here at the university. But the people stick to this field. So mechanical engineers first learns mechanical engineering and the basics. And at some point, we add a little bit of AI. And the AI students start with AI and learn a little bit about the applications. But what we need are people who understand both. And now you're facing the question you're putting here. In order to do this, you have to leave out some stuff. And take mechanical engineering, AI-based design, what we discussed here, will be an essential part of the job description of all engineers. And they need to understand this very early. So we have to leave out some stuff. But it's very difficult at the university. University is one of the most traditional conservative places on earth. So you have to convince your colleagues that some stuff becomes less important. And that's not an easy discussion at university. And so we train specialists in very traditional fields. And what we need as a society, my personal opinion, so subjective opinion, my personal opinion is people who have to be experts in new fields like AI-based mechanical engineering. So we always have the problem, we train experts in fields which we needed 50 years ago, but we should train them in fields which we need in 50 years.
It's an amazing finish. I didn't realize that I was going to ask you a question to which the answer, it's almost like I gave it myself 35, 40 years ago, because that's exactly the example I gave. What I did, what I had to do, I said on the left hand, there's civil engineering architecture. So you need to take the core, at least, in the finishing. And then on the right hand, there's informatics. Well, you need to take the core of that as well. And then you combine it. So it's almost like, and we said, and as you say, maybe we are conservative also, or specifically in the university space, at least these combined studies, they exist. So as long as we're open to that, we can allow people to come in with a maybe, informatics / AI machine learning curriculum, and on the other hand, do things within, the engineering space.
Yeah, exactly. So we should develop the training of people starting from the problems. If you want to build new buildings, bridges, whatever, where's, then you need a lot of AI. You need a lot of math. You need obviously a lot of civil and mechanical engineering. And so I think also and then it makes the people are much more motivated if they learn theoretical stuff because they understand they need it for a problem. And what we are very often doing is working the other way around. We first put a lot of theory into the people, and then at some point they later on they can use it. And people are motivated if it derives from the problem. And if you look from the problem side, you automatically have interdisciplinary mixed theoretical background: AI, machine learning, math, mechanics, fluidics. So you do automatically combine different fields. The problems are interdisciplinary. Our universities are not.
Oliver, thank you very much. To be continued at least 2 years from now, I would say.
Yes, hopefully we'll see each other before that.
You can start thinking about the topic we're going to be talking about in 2 years.
Yeah.
Oliver, thank you very much. Have a great day. Thank you very much for your great information sharing with our listeners.
Peter, thank you.
Thanks. Bye-bye.
Bye.